Hello, YouTube. This is Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. Today we're going to talk about the Bell inequality problem for conventional theories. And I'm going to annotate my original WordPress blog post here. Let's go right to Science Daily and take a look at this. The title of this piece is Looking Beyond Space and Time to Cope with Quantum Theory. Physicists have proposed an experiment that could force us to make a choice between extremes to describe the behavior of the universe. The proposal comes from an international team of researchers from Switzerland, Belgium, Spain, and Singapore, and is published in the October 28th issue in Nature Physics. It is based on what the researchers call a, quote, hidden influence inequality. This exposes how quantum predictions challenge our best understanding about the nature of space and time, Einstein's theory of relativity. So let's just skip down a little bit. The implications of the quantum theory have been troubling physicists since the theory was invented in the early 20th century. The problem is that quantum theory predicts bizarre behavior for particles. Well, here's an honest article. It is a bizarre theory, such as two entangled particles behaving as one even when far apart. This seems to violate our sense of cause and effect in space and time. Physics call such behavior, quote, non-local. It was Einstein who first drew attention to the worrying implications of what he termed the, quote, spooky action at a distance predicted by quantum mechanics. Measure one in a pair of entangled atoms, or photons or electrons, to have its magnetic spin pointing up, for example, and quantum physics says the other can immediately be found pointing in the opposite direction, wherever it is, and even when one could not predict beforehand which particle would do what. Common sense tells us that any such coordinated behavior must result from one of two arrangements. First, it could be arranged in advance, which is highly unlikely. The second option is that it could be synchronized by some signal sent between the particles. Of course, they're ignoring the solution of the reciprocal system, which we'll come to in a moment. In the 1960s, John Bell, hence the name Bell inequality, John Bell came up with the first test to see whether entangled particles followed common sense. Specifically, a test of a Bell inequality checks whether two particles' behavior could have been based on prior arrangements. If measurements violate the inequality, pairs of particles are doing what quantum theory says, acting without any local hidden variables directing their fate. Starting in the 1980s, experiments have found violations of Bell inequalities time and time again. So, of course, the conventional theorists concluded that quantum theory was the winner, it seemed. However, conventional tests of Bell inequalities can never completely kill hope of a common sense story involving signals that don't violate the principles of relativity. That's why the researchers set out to devise a new inequality that would probe the role of signals directly. Experiments have already shown that if you want to invoke signals to explain things, the signals would have to be traveling faster than light, more than 10,000 times the speed of light. In fact, to those who know that Einstein's relativity sets the speed of light as a universal speed limit, the idea of signals traveling 10,000 times as fast as light already sets alarm bells ringing. However, physicists have a get-out. Such signals might stay as, quote, hidden influence. Wow, what a loophole. Usable for nothing, and thus not violating relativity. Only if the signals can be harnessed for faster than light communication do they openly contradict relativity. The hidden influence inequality shows that the get-out won't work when it comes to quantum predictions. To derive their inequality, which sets up a measurement of entanglement between four particles, the researchers considered what behaviors are possible for four particles that are connected by influences that stay hidden and that travel at the same arbitrary finite speed. Mathematically, and mind-boggling, these constraints define an 80-dimensional object. Oh, really? The testable hidden influence inequality is the boundary of the shadow this 80-dimensional shape casts in 44 dimensions. The researchers showed that quantum predictions can lie outside the boundary, which means that they are going against one of the assumptions. Outside the boundary, either the influences can't stay hidden or they must have infinite speed. Well, I'm going to skip down. This is obviously so silly, it's beyond belief. So we'll skip down here. Here there are two choices. On the one hand, there is the option to defy relativity and unhide the influences, which means accepting faster-than-light communication. Relativity is a successful theory that researchers would not call into question lightly, so for many physicists this is seen as the most extreme possibility. The remaining option is to accept that influences must be infinitely fast. And that's a hoot. Or that there exists some process that has an equivalent effect when viewed in our space-time. The current test couldn't distinguish. Either way, it would mean that the universe is fundamentally non-local, in the sense that every bit of the universe can be connected to any other bit anywhere instantly. That such connections are possible defies our everyday intuition and represents another extreme solution, but arguably preferable to faster-than-light communication. Well, you can see this is pretty silly. So we're going to look at the reciprocal system solution. I'm going to go to MathCAD. Let's bring this up. Let's take a look at clock space-time and imputed coordinate space-time. Now for this analysis, let's imagine that two photons are created in a single event, and that they are initially one space-time location apart, and that they're moving in opposite directions. This is motion in clock space-time, the basic progression of the universe. The photons do not have any independent motion in coordinate space or coordinate time other than their linear vibration, of course. 2. In a gravitationally bound system in space, in our material half of the universe, the space progression is essentially neutralized, and so all we're normally aware of is the time progression. In a gravitationally bound system in time, in the cosmic or inverse half of the universe, the time progression is essentially neutralized, and so observers there would only normally be aware of the space progression. 3. Observers here in the material sector are moving with the time progression, but not moving in coordinate time, at least not at low speeds. Observers in the cosmic sector are moving with the space progression, but not moving in coordinate space at low inverse speeds. 4. Relative to our material reference system, the two photons appear to be moving apart in coordinate space, but not in coordinate time. Two photons thus appear to remain in adjacent coordinate time locations. Thus, if we perform some physical effect on one photon, the other photon will be similarly affected. This is true regardless of the amount of imputed coordinate space between the photons, and no signal is transmitted from one photon to the other across this distance. No signal. 5. Relative to the cosmic reference system, the two photons appear to be moving apart in coordinate time, but not in coordinate space. The two photons thus appear to remain in adjacent coordinate space locations. Thus, if they were to perform some physical effect on one photon, the other photon will be similarly affected. This is true regardless of the amount of imputed coordinate time between the photons, and no signal is transmitted from one photon to the other across this time. 6. Here then is the solution to the conundrum of, quote, spooky action at distance. In our material sector, the photons are still connected in coordinate time, whereas in the cosmic sector, the photons are still connected in coordinate space. In reality, of course, the motion of photons takes place only in clock space-time, not in coordinate space or coordinate time. So an effect on one will be an effect on the other. Seven. To compute the relative velocity of the two photons, we must use both imputations. If from the point of view of our material reference system, the photons move apart two coordinate space units in one clock time unit, the relative motion would seem to be a speed of 2, not 1, or c. However, from the point of view of the cosmic reference system, the photons move apart two coordinate time units in one clock space unit. We must therefore combine the two imputations to get the true relative velocities. 2 coordinate space units divided by 2 coordinate time units for the material sector velocity, or inversely 2 coordinate time units divided by 2 coordinate space units for the cosmic sector velocity. In both cases, the result is 1, or C, the clock space-time velocity relative to an imagined stationary reference system both in space and in time. So there you have it. The reciprocal system solves this conundrum of, quote, spooky action at a distance. Study the reciprocal system and prove it for yourself. You can find my work at Amazon.com and at transpowercorp.com. This includes The Unmysterious Universe, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything, and the reciprocal system, Microcosmos Database and Macrocosmos Database. Thanks for your attention.